colleagues, I'd like to open the final session. So this is a plenary session, and the chairman of our plenary session, Professor Alexander Tuzikov. So I give you a floor, if you do not mind.
Okay, thank you very much. I would like to announce our plenary session and the presentation towards artificial intelligence-based diagnosis of lung tuberculosis, TB portal, where traditional medicine joins forces with artificial intelligence, 3D visualization, genomics, and data mining. This presentation will be jointly done by Andrei Gabrielian and Dr. Vassili Kovalev. I would like to shortly introduce our key speakers for this session. Andrei Gabrielian is working in the National Institute of Allergy and Infectious Diseases of the National Institute of Health in the United States of America. He is a bioinformatics specialist with more than 30 years experience, studied and worked in Europe and United States, and he participated in many pioneering projects, including well-known sequencing and annotation of the first human genome project. Now Andrei is responsible for TB portal program in the National Institute of Allergy and Infectious Diseases, and he will tell about main activities done in framework of this project. Dr. Vassili Kovalev is working in the United Institute of Informatics Problems of the National Academy of Sciences of Belarus. Vassili has more than 30 years experience in the field of imaging, image processing, pattern recognition, and now he is head of laboratory of biomedical imaging in our institute, and he had a great experience working abroad in Germany, Korea, and United Kingdom, but came back and now is actively working in various projects, teaching at the Belarusian State University and doing many interesting projects with the students and master students of Belarusian State University. So I would like to give the floor now to Andrei Gabrielian. Please, Andrei.
Well, Andrei, we agreed to that. I'm doing kind of introduction, and then you're going specifically for TB portals. Is this correct?
Yes, I wouldn't call it introduction. You will be talking about real science, and then okay. I will just talk about the framework. Yes. Okay. Please go ahead.
Thank you, Andrei.
Please.
So that's part number one. The title you see, it's already voiced to the title, so let's go ahead. Let me start with a very brief introduction of our department, which is biomedical image analysis, and you see different kind of images we're dealing with, etc. And also, for the beginning, I will just highlight a couple of just two different research directions which we consider to be interesting, and we are doing something on that. So the first is using generative adversarial networks, so-called GANs, for generating of artificial medical images. Why should we do this? This is because the medical image, some kind of data which is very much restricted and prohibited by law to use in different scenarios, etc., etc. So the dream is just to learn how to generate artificial images to replace the real ones where it is possible. So that's on the left. It's shown, for instance, generating of artificial X-ray images of chest. And to understand why we need so many of them, why we need so huge database, that's very simple example. People are, patient could be male and female and somebody else, I don't know, but at least you need two, this case you need two different GANs to generate separately male and female. But also there are methods when you just supplying the image as such and saying the kind of a switch, which saying gender of this person, and then you train in one GAN, but in limit, in our case, we also examine different ages people for 1 year of life from 20 to 30. That means we've trained 50 GANs, what is difficult. And so we tried different approaches which already exist. The first, and I would say classical, but classic is just few years for this classic. It's so-called deep convolutional GANs, and we produce images like that, which are not bad. And then we also tried so-called progressive GANs, pro-GANs. So they start, in this case, the image starts from just 4 by 4 pixels, and then they are subdividing and getting more fine and more refined, and then finally the process stops. And we found that this still works better in this particular case. So we put all these services, and not only this one, but other also in our website, which is called image.org.by. And I invite you to visit that functionalities, try, criticize, etc., because not everything is working perfectly here. It's just, artificial histological images looking nicely, but that image is, we are trying to do post-processing, not just generate from random vectors. And another problem which we are researching in is are adversarial attacks to deep convolutional neural networks. So deep means sounds like it's good, they are deep, but it's create more and more chances for adversarial attack. The attack is done by modifying our original image, modifying in the way to make it, to force the neural network to make a wrong decision. Like a healthy person will be diagnosed as a pathology and CT and X-ray and some other, like this one, histology. So on the left, original, on the right, it's modified. It's unlikely you will find the difference, but the cancer, that's the clearly cancer, and then it's diagnosed like norm, and vice versa. So that's a very important problem, and we examined both scenarios like black box and white box attacks. Second case, we know the architecture of the network which we're going to attack. So that's original images again on the left. On the right, it's attacking image. And we examine different kind of architectures on different kind of images, not only this one. Don't think this way. It's more than 1 million images in total involved in this experimentation. So that's the quickly what we are researching on. Now let me start the main part of my part, which is lung disease diagnosis, and specifically tuberculosis. By the way, we need to understand that there is not just something specific tuberculosis, and that's in lung. There are different kinds of abnormalities in lung, which may and may not be associated with tuberculosis. So we may not be so narrow. We need to be broad to cover the problem of diagnosis of lung tuberculosis. And this is naturally subdivided for screening, like screening in most of the countries where it is, it's done by X-ray, except United States, where it's done by CT. And treatment, where normally doctors radiologists using computer tomography. So we will be talking about both of them separately right now. So in our country, for instance, it's already mentioned somehow that we have a massive screening, which is lasted more than 10 years, and it's computerized. That's naturally, natively digital images. They come in by network to certain medical hospital, and then the results going back. And first, to start with the lung diagnosis, we need to extract lung first. So that's commonly known problem of segmentation. We are working many years already on the problem. We start with the classical approaches, and then with this nonlinear image registration segmentation based, on which the segmentation is based. And then last years, we are more and more on the using the convolutional neural net architectures of different sort, and of course combining all the advantages where it's possible of another approaches. That's a figure which just illustrate, you will immediately recognize this is something like UNet. So UNet is now much wider. People who doing that, they develop it further, but nevertheless. So that's example of lung segmentation, which just first step to do something with lung. We need to extract it first. Then that's very briefly about our solution. So the solution is not just first, not the second. There are several solutions, and we gradually improve our quality of diagnosis using different kind of architectures, different kind of network and combinations of them, and so on and so forth. As already Vassili in previous talk, the member of my group, former, we, doctor and everyone actually not need just only probability of abnormalities or lesion in the lung. The person need also to point out where it is. So we producing, along with that probabilities, we also producing heat maps to point out the attention where the decision comes from. You see, one is totally good, another one is so bad, I mean lung. So that's examples of heat map. They're very first, but I like them how they appear. The heat map is not cut just to remove everything except lung, but still it looks nicely in my view. And this, this solution is now available for free on our website, so you can upload your own image and get the result. And already there are 2 countries, except Belarus, 2 abroad countries who doing that and testing their own images. And that's, of course, technical problem, because for different format, different traditions to store the images, all that kind of things. So the second portion, second work, that's CT, computer tomography. And we detecting, we need to automatically detect lung abnormalities. They call lesion in English. And I will first tell you about data preparation. So it's roughly 3 stages. First stage is just identification of cases which are of interest. This is naturally different kind of abnormalities coming with very different frequencies in hospital. So to have a balanced data set, a good quality data set, we need to identify which patient is interesting, which is not interesting, just to get the result. And then second stage, which is done by high quality radiologists who is working with us and Andrei and with all our project. And he pointed out different kind of lesions, and then trained non-radiologists, they doing final wording, because we need in many occasions. And this is the kind of lesions which we are dealing with. And at the very last time, we also include COVID-19, which is a general disaster nowadays. So, and as usual, the segmentation, the analysis starts from segmentation of lung. Some people doing segmentation of lung a couple of times on healthy subjects. It's going pretty straightforward, pretty well. Believe me, in norm, everything is going much more easy. But in case of pathology, then the problem really starts. It's really difficult to accurately segment the lung itself. And then we need to go inside the lung and to find out lesions, abnormalities. And that's it's also done with the neural network. It's also available now, you see, it's also available now from our website. Of course, CT is heavy image, and there are some limitations. You need to good internet to upload. You need to permission for dealing with this patient to put it somewhere outside of your office, etc., etc., etc. But it's not our end. We need to just deal with them. And of course, you on website, you would be able to review somehow the segmentation results. So there is a kind of viewer, which is also web-based viewer. You can do it just from your computer without installing any software. Once we got this kind of extraction of and estimation, the quantities of lesions, of abnormalities in lung, then we can do also content-based image retrieval. But this is retrieval not just similarity retrieval by visual appearance. It's medically meaningful searching, which is capitalized on the information on how many lesions, where they are, how big they are, etc., etc. Then the similarities, it's treated also would be supported by doctor. Otherwise, it's visual similarity may help, but may not. Last times we also looking at lesion segmentation with lesions which are associated with COVID infections. So that's on the left. You see, recently we take part in a large international competition, and we got in top 10 and with the position number 6. So on the left, you see the lesion which is segmented by doctor. On the right, you see the lesion which is segmented by software, and that's the approved. That's some certificate which says that this particular member of group was leading that submission, that development. Actually, we submit 3 different solutions. So that one was the best. And I think all top 10 now using UNET, and then clever guys from Heidelberg, from German Cancer Research Center, the KFC. They introduced new versions, and NN-UNET, it's a version of UNET, which is optimizing parameters by itself. So you know that problem. It's also somehow included in the last version. And finally, I came to the point when I will give the floor to Andrei, but before that I will just in 1 minute, I will click on our website. So that's image.org.by, that's the team, and that's different kind of things we have put there, like this CT diagnosis online. You see the result, then you can register and see in more details. And also Andrei will add what is possible to do in portals, because they are large nowadays. And that's okay. Daniel, you was interested about histology, so that's in spare time. I can show you how does it works. It's also available from web, so you can that blood. That's the blood clearly, etc. And then you can do something like a classification, etc. Right here. And also, you can upload your own. I will not do this. I will just do that. Yeah, it's clear. It's good. So that's it, Andrei. Now it's your turn. I will stop share my screen.
Thank you very much.
You're welcome.
Now let me see what I can do here.
By the way, within my 15 minutes.
Okay.
Yes, now we
So
see
I want to switch gears now and tell you about tuberculosis portals, our international program and resource that supports research and integration of artificial intelligence predictions among other data types for better understanding and more efficient treatment of tuberculosis. Why we are so interested in tuberculosis? Clearly, from point number 2, we are living in the 21st century, and yet TB manages every year to claim more than 1 million lives. Now, if you extrapolate that figure to human history, you will see how terrible and damaging the disease was for the humankind. The World Health Organization launched its End TB strategy in 2014 with the aim to cut TB incidence by 90% by 2035.
Excuse me,
Gabrielian. Let me switch to the slideshow.
Yes, exactly. It's better to switch to widescreen.
I'm sorry.
That's okay.
Let me see now. Can you see my screen?
Yes.
Perfect. Yes. Now, WHO reminded us, in the words of Dr. Teresa Kasayeva, Director of Global TB Program, that enhancing and optimizing global data sharing efforts is critical to make the most of the existing evidence. We cannot beat tuberculosis alone. No country can do that. So only the joint efforts can do that. And this is why TB Portal Program was spearheaded by National Institute of Allergy and Infectious Diseases. Our mission was to create a network of global shared informatic resources to advance the understanding of tuberculosis as a disease and to contribute to the development of new and efficient early diagnosis and improved treatment with an emphasis on multi-drug resistant tuberculosis, the worst kind of tuberculosis that does not answer well to most efficient drugs that we have right now. We started years ago, and I'm glad to tell that the first hospital and the first institute that joined the TB Portals program were from Minsk, from Belarus. Currently, we collaborate with doctors and researchers in 15 countries, and we have also discussions with 3 additional countries. Here is the map that gives you the outlook on our sites worldwide. Next slide gives you some view on how many cases we have now. We are closing on 10,000 cases, 10,000 records that are pretty complete. They're patient-centric data, meaning that we know everything about the patient. We know the microbiology, we know the clinical data. On the right side, we can see that we also collect genomic data about the pathogen. We have imaging, and what is important and what is unique for our database, that we also store and present the artificial intelligence-based annotations of these images. We collect biochemistry data, and we also venture into new domains, including transcriptomics and microbiome data. Here, on the next slide, we see the schematic view of how the program works. It all starts with the data collection that is on top. People send us the data. The centers send us the annotated data. Then we and other researchers analyze the data. So essentially, we're doing the extracting knowledge from the data. And with this knowledge, after the analytics part, we are trying to answer important questions that doctors working with tuberculosis might have about the diagnosis, about genomic evolution of pathogen, about the factors that are associated with successful or unsuccessful treatment, etc. Importantly, TB Portals program makes all data that we collect together with computed data and predictions, which is our added value, openly available for research purposes. Of course, we don't collect personal data or share them, and we closely monitor the anonymity of all tuberculosis patients that we have in the database. We provide downloads of entire database or its parts via Aspera or APIs. We develop our own open access tools and resources where people can analyze TB Portals data and their own data. So here is one of our resources. It's our cornerstone. It's a case browser, which works pretty much like the collection of records of data from tuberculosis patients. And it also includes the annotations that were done by the algorithms that were described by Dr. Kovalev. Here is probably you cannot see because it's kind of a low resolution and too much information on one page, but every page, every record has the data for individual patient that consists of socioeconomic data, drug susceptibility testing, treatment history, outcome, comorbidities. Very important on the left side, you can see the time line of the treatment and tests and radiological investigations that were done during this course. Now, coming closer to the images that we're talking about, we have several kinds of annotations. We have annotations provided by radiologists, and we have now the artificial intelligence labeled lesions annotations. So some might ask, why are we so interested in artificial intelligence and these algorithms? The truth of the matter is that annotations by radiologists are very diverse, and there is no good consensus. This is not my opinion. This is known historic fact. So clearly, in tuberculosis and in other diseases, there is a need for the precise, general, and very stable artificial intelligence supported predictions of various features associated with the diseases. Here you can see an example of the record that has been annotated by artificial intelligence. You remember this from previous presentation, how it was done. For tuberculosis cases, we have predictions of various features associated with tuberculosis, such as foci, caverns, fibrosis, pleuritis, atelectasis, and pneumothorax. They are color-coded and overlaid on top of existing slices of CT images. And also we have the similar images for each of the annotated images, again, as presented by Dr. Kovalev. Now, we, of course, were testing the predicted and manual annotations with the ultimate goal of our database and our research project, namely how all this correlates with the treatment outcome. Because if we can compute features that are highly correlated with the outcome, then we can flag soon enough the problematic cases and help doctors to identify necessary changes in treatment and so on and so forth. So we published some papers. This is one of the recent ones where we analyzed how the treatment outcome correlates with the computed tomography observations provided by radiologists, and we found pretty good correlations. So it was very good results. And this is why we enthusiastically support further integration of both radiologist and artificial intelligence annotation into the TB Portals program. Once again, this is what makes our TB Portal database unique. Now, in many countries, CT is still too expensive for mass screening, but fortunately, X-ray investigations are cheap enough and plenty informative. TB Portals also collects X-rays together with CTs for histories of disease. And years ago, we joined forces with a company from India called Cure AI that developed AI-based X-ray analysis system for TB diagnosis and predictions of TB-related features. So their database was very extensive, hundreds of thousands of X-ray images, but India had mostly drug-sensitive tuberculosis. So we're not sure how it would perform on our database, which is rich in drug-resistant cases of tuberculosis. First thing that we did, we checked their predictions in our database, and results were pretty good. Turned out to be very promising. Here is the publication that pretty recently supported the integration of Cure AI annotations into TB Portal's database. And very fresh news. So this is a September publication of this year, where Cure AI together with other 4 prediction systems were tested on pretty large data set. So it was 23, almost 24,000 individuals that were included in the analysis for prediction of tuberculosis. And what is interesting, that is all 5 artificial intelligence algorithms significantly outperformed the radiologists, but only the algorithm that is that was done by Cure AI and another algorithm that was provided by CAD for TB, were able to meet the WHO's recommended target product profile of triage tests, which is more than 90% sensitivity and more than 70% specificity. So we are looking forward to continue this collaboration as well. Now, diagnosis of tuberculosis is not the end game, because even when diagnosis is right, and the treatment can be problematic, and the cure rate can be, especially in cases of multiple drug-resistant tuberculosis and extensively drug-resistant tuberculosis, is about 50% and could be as low as 30%. So it's very important to analyze continuously what is going on with the lungs. And this is where we are moving with our collection of the data, trying to build models that would tell us and doctors in advance if something is going wrong. Also, even when the person is seemingly healthy and released from the hospital, there are some chances, and depending on the country and TB burden in it, from 5 to 30% chances that TB may relapse. So again, we will be looking at CTs and X-rays for additional information about whether the patient might still have something in the lungs that would be evidence of tuberculosis not being completely cured. So these are our directions for the future. So this is why we are increasingly getting into the investigation of disease dynamics. So we are toward the analogy where moving from photos and snapshots to movies. And here is an example of morphing of several consecutive X-rays from the same patient. So on the right side, which is the left lung, you can see on the top that the cavity, which was pretty prominent in the beginning of treatment, shrinks towards the end of the treatment. So, and this is great, this is good. We know that the treatment works and the patient has been successfully cured, but it's not always the case. So making these movies, videos, and presenting them to doctors and students is very important and informative. Lately, we were going even further with 3-dimensional images. So From CTs, we begin to develop three-dimensional models of lungs from TB Portal's collection. And of course, we attach the information about treatment, timeline, clinical findings, so it all is integrated together. This is a snapshot of a three-dimensional model that we have. So this is 45-year-old male smoker, initially diagnosed with tuberculosis, empirically treated for drug-sensitive tuberculosis. And you can see that in the lungs, this is the radiologist-provided annotations, there was a fair amount of infiltrate and the foci that were in the right lung here. However, after the treatment, 1 month into treatment, we can see that the bad area shrinks significantly. And we know that over the course of 2-year therapy, this patient was successfully cured. Now, that was manual annotation. And we were, of course, interested how the artificial intelligence annotations provided by Dr. Kovalev's group will work in this case. And they worked pretty well. So they identified very nicely the area where the infiltrate and fibrosis was located, and also correctly identified the shrinking of the bad area into treatment. So clearly, artificial intelligence predictions, as we saw from X-ray example and CTs, have good future and very promising future, and we will continue to integrate this information into our resource. This model and other models are already available for everyone on our TB portal. We're working on 10 additional models that will highlight various forms of tuberculosis and types of treatment. You can come and see for yourselves. We'll be glad to hear from you and answer your questions. With this, I want to thank you for your attention, and also thank my colleagues and friends, the great TB Portals team that continues to work on growing, improving, and expanding our data and our resources. Everything that I presented today is, of course, teamwork. All the best. Stay safe, and hope that next year we'll all be able to meet in person in beautiful Minsk. Goodbye.
Thank you very much, Andrei, for your very interesting presentation. We would like to ask participants of our conference to ask some questions to you. Okay, please, colleagues.
I see none.
No.
Yeah.
Maybe I can ask one question. Could you say, Andrei, as it follows from your presentation, so it's possible with high probability diagnosis tuberculosis by X-ray images, or it isn't? I mean that
it's possible
to say from X-ray images whether it's tuberculosis or pneumonia or maybe other lung diseases. So it's possible or not? I haven't understood now.
Okay, my question. No, I cannot answer a question with questions. So I will tell you, it depends. It depends on how long the disease was taking the course. If the person was just infected with tuberculosis mycobacteria, then the damage for the lungs is not done. The pathogen is already in the system. Your immune system already responding to it. You can find the pathogen in the sputum, but the lungs might be still not damaged. In this phase of the disease, it's difficult to diagnose anything. However, as the disease takes its course, the small nodules and then further the larger cavities might appear in the lungs depending on the host. And then it's easier and easier and easier to see that, yes, indeed, this is tuberculosis. So depending on how bad is the situation, it's either very difficult or very easy to diagnose tuberculosis. So one test, X-ray or CT, is not enough. It always probably will be a combination of microbiological methods, blood tests, and radiological information. Sorry for the long answer.
Okay, thank you very much. And another question is concerning TB portal. So this portal contains various information, clinical data, images, genomic data. And do you know whether for other diseases similar portals are available in the internet, or it is a unique portal for TB?
I'm happy to say that it is a unique resource. And as I said, it is patient-centric. So if the patient is in TB portal, we know everything about this patient. And it means that we know, for example, images, and we know the genomic content, the genomic outlook of the pathogen that invaded this person. We also know the lab tests and so on and so forth. We do not artificially grow our database. We do not download, for example, additional genomes from GenBank because we don't know anything about the patients from which these pathogens have been sequenced. And therefore, we cannot make any inferences, like, did this patient died? What kind of drugs he was treated with? How long into the treatment this pathogen has been isolated and sequenced? So we are trying to create the unique database, which is the most complete and productive database for research. And as I said, I would like to express my admiration for the support that we're getting from our researchers worldwide. And the collaboration with Belarusian team has been extremely productive and fruitful. Thank you very much for your support.
Okay, thank you very much once more for your presentation. We will see whether there are any other questions or no.
No, we have none. Yeah, we have none also in chat.
So we can finish our plenary session. I would like once more to thank very much our distinguished speakers and for this excellent presentation and this excellent job. Thank you very much.
Thank you. So in my turn, I would like also to thank you, dear Andrei, that you was able to be here in afternoon session. So now, according to the lag with the USA, so you have completely different time, but still. So yeah, now we see your face. Okay, that's good. Finally, well, on this note, quite nice high notes. I'd like to say thank you to all of you. So we have very productive session. Now we can finish this day. And say to each other goodbye and see you tomorrow. But before you will disconnect, I would like to say that in 1 hour we will start our informal meeting, let's say virtual cafe. The link is in your emails, or as for audience, YouTube audience, you can just chat. You can drop a message to the Telegram chat, or here in YouTube chat on Zoom at the moment. So I will send an ID. You can join us to spend some informal time on the internet cafe, which is provided by Busnet and Jan Severus Edumit. So now I'm only one who's between you and evening. So goodbye. Thank you. See you tomorrow.